let us look at chapter 12, inverse functions. To define an inverse function, we need to know what a one-to-one function is, first of all, right? I think we have defined one-to-one functions before, but just in case you have forgotten, a function f from a to b is called one-to-one, is 1 to 1, which is generally denoted 1, 1. If f of a is equal to b is equal to f of a prime implies a is equal to a prime. That is to say, if a and a prime have the same image, then a has to be equal to a prime, right? This was an important thing when we were looking at f of union of images and intersection of image of intersection of sets, right? A function f from a to b is called onto if for every b in b there exists an a in a such that f of a is equal to b, right? Basically that means every element in b has something that is mapped to it. It has a pre-image. This is also called surjective, and this is also called injective. Okay, so one-to-one is also called injective, onto is called surjective, and if it is both injective and surjective, it is called bijective. A function f from a to b is called a bijection, or the function is said to be bijective if f is both 1, 1, 1, 1, and onto. Okay, which is to say it is both injective and surjective. That is why it is called bijective. Okay, now that I have functions which are injective and bijective, injective and onto or surjective, you can, even if a function is not injective, you can possibly restrict it to a certain domain to find where they are injective. Okay, so for example, restrict the function to a suitable domain to make them 1, 1. Okay, so for 1, f of x is equal to x squared, right? So generally f of x is equal to x squared is not injective on R, right? Because as negative x squared is equal to x squared. But if I say that, oh, in my domain of the function, I don't have negative x, I only have positive x, then there is no problem. Injective on 0 to infinity or negative infinity to 0, right? If I restrict it to any of these two domains, then it is injective. I can further restrict it. I could take from 1 to 7 or something, and it would still be injective because that lies within 0 to infinity. Or I can take proper subparts of these where it would be injective, but this is the biggest intervals that I can find where it is injective. Okay. Second, f of x is equal to sine x. Again, it is not injective. Not injective on the domain, which is R, right? As sine of, let me say, as sine of x is equal to sine of x plus 2 pi, right? If I draw the graph of sine x, right? It is hitting back after 2 pi. It is repeating after 2 pi. But that does not mean it is not injective even on 0 to 2 pi. Even if I restrict it to 0 to 2 pi, right? If I restrict it on this interval, it's still not 1 to 1 because, for example, these 2 points have the same value, right? However, if I do restrict it from this interval, which is negative pi over 2 to pi over 2, then it is injective. So injective on negative pi over 2 to pi over 2. Okay. Or you could have taken pi over 2 to 3 pi over 2, whatever you want. One of these two would work. Okay. I'll let you work out what to do for f of x is equal to log of x. Okay. You can also do this by horizontal line test. Also, can also figure out whether 1 by horizontal line test. Horizontal line test. What is the horizontal line test? Well, it is the similar as the vertical line test that you have seen before. A function here, okay. Too big. Suppose I have a function like this. Okay, compared to a function which is like this. Then I can figure out if the function is 1 to 1 or not by drawing a horizontal line. And if any horizontal line crosses the graph multiple times, then the function is not 1 to 1. Okay. So in this case, intersects more than once. Intersects more than once. Therefore, not 1, 1. Here, no line intersects more than once. No line. So I'll call this figure A. B, no line intersects. No horizontal line. No. B. No. Horizontal line intersects more than once. Therefore, it is 1, 1. Therefore, 1, 1. Okay, so that's the horizontal line test. That if a horizontal line intersects the function more than once, then it is not 1, 1. If no horizontal line intersects it more than once, then it is a function, one-to-one function. Similar to the vertical line test, which says, oh, if there is at least one line which intersects it twice, a vertical line, then it's no longer a function. In that case, we can define what the inverse function for a given function is. Definition: for any function f, for any function f, the inverse of f, denoted f inverse, is the set of all points, pairs b comma a such that a comma b, such that the pair a comma b is in f, right? Similarly, our definition of a comma b, a pair a comma b in f, was that b is equal to f of a, right? So this is my formal definition of f inverse. Note that this does not guarantee that f inverse is a function. F inverse here is a set, and this is fine because we defined pre-images, right? We were looking at unions and intersections of sets, intersections of images, and at that time we did define f inverse, and we looked back that, oh, f inverse could be multiple elements, so it need not be a function. Generally, at least. Theorem: f inverse is a function. F inverse is a function if and only if f is 1 to 1. F is 1 to 1. So this is the shorthand way of writing if and only if. I think I have written this in class before. If and only if. Okay, but in case you haven't seen it before, this is, I'm going to define it this time. I will be continuing to use it henceforth. Okay, proof. What does it mean by it to be a function? Well, suppose f is 1 to 1. Suppose f is 1, 1. Okay, I want to show that f inverse is a function. Suppose not. So suppose a comma b and a comma c belong to f. Okay, f inverse, my bad. So suppose both of these belong to f inverse. Then, therefore, b comma a and c comma a belong to f. Therefore, f of b is equal to f of c is equal to a, and therefore b is equal to c, right? And therefore a comma b is equal to a comma c, and therefore f inverse is a function. F inverse is a function. Okay, let me just do this so that it fits in one page, just because I don't like this being going down. Suppose a comma b and a comma c belong to f inverse. Okay, so then I get that it is a function. Yes, it is a function, right? Now suppose it is f inverse is a function. I want to show it as an injective. suppose f inverse is a function and f of b is equal to f of c, right? Then f contains pairs b comma f of b, b comma f of b, and c comma f of b, c comma f of c, c comma f of c, but c comma f of c is equal to c comma f of b. Therefore, what do I get? F of b comma b and f of b comma c belong to f inverse, right? Well, that can't happen because f inverse is a function. The only way this can happen is if therefore b is equal to c, right? Because it's a function. F of b cannot have two different images. B has to be a function, as f inverse is a function. Therefore, f is 1, 1. Okay, so we have shown both ways that if f inverse is a function, then f is 1 to 1, and if f inverse is 1 to 1, then f is a function. So, how do we get the graph? The graph of f inverse in terms of graph of f. Okay, so suppose I have my function f, which goes maybe like this, right? How do I get the graph of f inverse? So this is f of x. What you do is you reflect around the line y is equal to x. So this is my line, like this is my line y is equal to x, and I am going to invert the graph around y is equal to x, because what is happening? A point a comma b, if a comma b belongs to f, then b comma a belongs to f inverse, right? I am flipping the coordinates of each point, and that is the same as flipping it all across the y equals x line. And so I'm going to get a graph which looks like something like this. Okay, this is my f inverse of x, right? So the easy way is you just flip the graph across y equals x line. Okay, if you had a piece of paper that you were drawing it on, you could basically turn it one way and yeah, let's not go with that one. It's hard to demonstrate, but this is how you get it. Okay, now this also tells you that, oh, if I were to trying to find f inverse of f of x, right, then I get that. How would I take the graph of f inverse of x? Sorry, f inverse of x. Well, I would again flip it at y equals x, but that would give me back f of x. And therefore, note, f inverse of x is just f of x. Therefore, f inverse of f inverse, sorry, that's stated wrong. I wanted to say f inverse inverse of x is just f of x, right? Which is to say that therefore f inverse is equal to f, right? And this is exactly the same as saying that, oh, if I look at what are the pairs in f inverse, it's AB. Suppose f has pairs AB, then f inverse has pairs BA. If you look at inverse of that again, that's again going to have pairs AB, which is the same exact thing as what you had in f. Therefore, you get that f inverse of f inverse of x is equal to f of x. Okay, corollary. Suppose f is 1 1 on A, then f of f inverse of y is equal to y for every y in f of A, and therefore f of f composed f inverse is equal to identity on f of A, right? Similarly, f inverse of f of x is equal to x for every x belonging to A, and therefore f inverse composed f is equal to identity on A, right? I am not really going to prove these because it's just diagram chasing. You say that, well, if f is 1 to 1, and then call f inverse of y is equal to x, f of x is by definition y, so f inverse of f of y is equal to y. The function that does that is identity. Similarly for the other one. Okay, so proof, left as an exercise maybe. Proof left as exercise. It's really easy. Just say that f inverse of y is equal to x. You'll get it. Similarly for the other one, do f of x is equal to y. You'll get it. Okay. Then theorem 2. If f is continuous and 1 to 1, if f is continuous and 1 1 on an interval, then f is either increasing or decreasing on that interval. Then f is either increasing or decreasing on the interval. Okay. The important part is it has to be continuous, otherwise this does not work. And the proof is relatively simple. Yeah. Where did we go? Okay. How do we prove this? There are 3 steps. 1, suppose A is smaller than B is smaller than C, then either A is small, then either f of A, so let me call this as 1 rather than 1. Either 1 f of A is smaller than f of b is smaller than f of c, or 2, f of a is greater than f of b greater than f of c. Okay? Why is this true? Suppose I had that f of a is smaller than f of c. Okay? And then it becomes a question of whether f of b is smaller than f of a or not. Okay? So suppose and f of b is smaller than f of a. Then intermediate value theorem, then IVT on in the interval b to c would implies there exists an x in b to c such that f of x is equal to f of a, contradicting 1, 1. Similarly, if f of b was greater than f of c, then I can get the same exact condition on a to c. Then then IVT on a to b implies there exists x in a to b such that f of x is equal to f of c. Right? In either case, this is contradicting 1 to 1, and therefore I have to have this. Right? Part 2. If instead of 3 points, I take if a is smaller than b is smaller than c is smaller than d, then first, then either 1, a f of a is smaller than f of b is smaller than f of c is smaller than f of d, or 2, f of a is greater than f of b is greater than f of c greater than f of d. Okay? Proof by applying 1 to a, b, c and b, c, d. Okay? So I apply it to any of these two, I get this. And now that I have this for 4 points, take any 2 points. Take a smaller than b. Suppose f of a is smaller than f of b, right? Then f is increasing, I want to show. Then want to show f is increasing. How do I show this? Well, take c comma d in a take c comma d and apply 1 to and arrange a, b, c, d in ascending order, in increasing order, and apply 1. And apply 1. Similarly, if f of A is greater than f of B, right? As soon as you take C and D, you can see that, oh, either these 3 points have to have it increasing, or the 3 points have to have it decreasing, and in either case, my function is consistently increasing or decreasing. So let us do some examples. Example: suppose f and g and suppose f and g are increasing. Suppose f comma g are increasing. Are the following increasing? First, f plus g. Second, f times g. And third, f composed g. Okay. I am going to give you a hint. I'm going to do only the third part. Okay. And I'm going to give you a hint for second part. Hint: look at f of x is equal to x when x is smaller than 0. Okay. Now, how do I show f of f composed g? Suppose a is smaller than b, right? Then because g is increasing, g of a is smaller than g of b. Therefore, f of g of a is smaller than f of g of b, right? And therefore, that is increasing. Similarly, if f composed g, if plus g I'm looking at, then I get let a smaller than b. Therefore, f of a smaller than f of b, g of a smaller than g of b. Therefore, f plus g f plus g of a should have left more space, is smaller than f plus g of b. Okay, because if you expand these out, you get f of a plus f of b, g of a plus g of b, and both of them are individually smaller. Yeah, whatever. I'll leave it at that. Okay. Okay, I'll stop this video here, and we'll continue in the next part.